All right, starting section 5.2 today. Another fairly long list of problems from the textbook, but only 3 problems from WebWork this time, so maybe that'll balance out. Okay, so we talked about angles in section 5.1, and now we're going to talk about trigonometric ratios. Trigonometric has got a few too many syllables, so we usually just call them trig ratios. So the starters, and I don't mean just first, I mean to say the most important ones, the ones that we use most often, will be sine, cosine, and tangent. Okay, so these ratios are defined for an acute angle in a right triangle. So the little square down here says it's a right triangle, and then either of the other angles is called acute. It doesn't have to be the smaller of the two, it's just not the 90. So for this acute angle theta, the first thing to do is identify the side that's opposite the angle and the side that's adjacent to the angle, and then also the hypotenuse of this right triangle. Okay, so now that we've got this angle pinned down, we talk about the trig ratios for this angle. So the sine of the angle is the length of the opposite side divided by the length of the hypotenuse. Cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent side. So again, they're all ratios, this is why they're called trig ratios. There's a mnemonic for this, a memory device, SOHCAHTOA, sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, and tangent, opposite over adjacent. SOHCAHTOA. I've heard others, but I think that's the old one, the oldest one I know. Okay, so just an example then. Angle theta, labeled down here. This is an acute angle in the right triangle. So the sine of theta is defined to be the ratio opposite, which is 2. I should make that clear. The side opposite the angle is this one. The side adjacent the angle is this one. So sine is opposite over hypotenuse. The cosine is the adjacent. That's length root 5 over the hypotenuse. And the tangent is the opposite over the adjacent. Okay, first 3 trig ratios. Okay, so here come the bench players. Sometimes important, but certainly used less often. These functions, and I should have written out the full names. This is the cosecant, the secant, and the cotangent functions. Now, actually in your book, they give slightly different definitions. They'll give the definitions in terms of ratios of the sides of the triangle, but I think it's better, at least I found it better, just to think of them as reciprocals of the starting trig ratios. So cosecant is 1 over sine, secant is 1 over cosine, and cotan is 1 over tangent. Actually, now that I'm looking at this right now, I think there's a chance that our book defines this simply as COT and not cotan. Okay, so let's try that out again for the same triangle here. So cosecant, 1 over sine. So if you remember, sine is the opposite over the hypotenuse, then you'll get the reciprocal here being 3/2. So as I said, our book defines the cosecant actually in terms of sides. Our book defines the cosecant as hypotenuse over opposite. And you can think of it that way as well, but like I said, I usually just compute the sine and take its reciprocal. Right. Same thing here for the secant. I'll compute the cosine of the angle theta. That's root 5 divided by 3. That's adjacent divided by hypotenuse. And then taking the reciprocal will give me the secant. Square root 5. Okay, last one. The tangent. Tangent is opposite over adjacent. So maybe without going to the fuss this time, I'll just say that the cotangent then is the adjacent over the opposite. All right. Yeah, so part of what I was saying right here about each of these bench players having their own defined ratio, I'm writing out right here. So if you want to see the formulas, oh, sorry, I have them in a strange order comparatively. The cosecant, I said, was hypotenuse over opposite, and it's right there. Yes, I just got a glimpse at the text here. They do call it just the COT. I don't know how to abbreviate that. The cotangent. The problem with these ratios is, well, I can't think of any good mnemonic to try to explain these ratios. Doesn't mean you can't just memorize them flat out, though. Secant is hypotenuse over adjacent. Yeah, I don't know. Okay, so we've just defined the trig ratios for an angle in terms of lengths of sides of a triangle. So we have this slight worry that if the same angle is appearing in two different triangles, we'd like that the trig ratios are the same for both. So here we're trying to illustrate that possibility. The angle theta is appearing in this right triangle, but it's also appearing in this right triangle, and we'd like to make sure that the trig ratio, say sine, is the same for both of these. We want it to be the sine of the angle, not a particular triangle. And the reason this works out is that if this acute angle is the same in both triangles, then the triangles are similar, and that means that one is just a scaled up version of the other, and that says that the lengths of their sides will be in the same ratio. So the sine here, opposite over hypotenuse, is computed as 3/5. In the scaled up version, the sine is computed as 30 over 50, which again reduces down to the same number, 3/5. Okay, so this is a type of problem in your book, and also in a webbook problem, so I've got to make sure you know how to do it. I'm not sure that I can think of an immediate application, but it does kind of test your knowledge of trig functions, so we will do it. And problem number 23 in your book is quite similar to this. So you're asked to sketch a right triangle with an acute angle theta, where the cosine of that angle is 3/4. Right? And then once you do that, your follow-up is to compute the sine and the tangent of that angle. Okay, so when you get this type of problem, this is what you want to do. You want to sketch a right triangle, but don't worry about the scale too much. I usually, I guess, have mine a little shorter and a little wider than it is tall. Okay, and then label one of the two acute angles with whatever letter they gave you. And for angles in general, I guess it's pretty common to use Greek letters. So they said the angle will be called theta. So I'll just pick the lower left angle. It's got to be the acute angle. Okay, so identify now. This is the opposite side. This is the adjacent side to theta. And what they've prescribed here is the cosine. So we just learned it, but the cosine, so katoa, that's the adjacent over the hypotenuse. So what we're going to do is, in our triangle, label the adjacent side, the side adjacent to theta, with 3. Oh, I thought I was going to do that. I'll come around to it. And the hypotenuse, 4. Right? So somewhat amazingly, this now is a triangle where the cosine of theta is 3/4. Okay. Right, so what we need to do now in order to be able to compute the sine and the tangent, both of those, of theta, both of those require knowing the opposite side of the angle. Sine is opposite over hypotenuse and tangent is opposite over adjacent. So we need this third side. And the way we get that is to use the Pythagorean theorem. Okay, so we have 3 squared plus b squared equals 4 squared. And if you do the arithmetic there, I think that's b squared equals 16 minus 9, which is 7. And so this b side here, so it's just not working to click in there. I wonder what that is square root 7. Okay, this third angle isn't terribly important to us, so I'll just blank that one out. Okay, so now with all the sides labeled, we can go on to compute the ratios that were requested. So sine of theta, that's the opposite over the hypotenuse, and that's here root 7 over 4. And what else did they want? They wanted the tangent. Yeah, we're only using the bench players here, only the starters in it, none of the bench players. Okay, so this is the opposite, square root 7 over the adjacent side to the angle. Okay, so it does exercise quite a few things here, so some practice problems like that. Maybe put in a timestamp here. Where are we? Oh, not too bad. 11:30, let's say. Okay, so there are 3 special angles where we are able to construct triangles with these specified angles, and consequently we'll be able to compute the trig ratios exactly for these 3 angles, 45, 30, and 60. So let's first look at the 45-degree angle. So in order to compute the trig ratios for this angle, we need to construct a triangle that has a 45-degree angle as one of its acute angles. And one clever way to do this is just to start with a unit square, that is 1 by 1 square, and draw a diagonal. Now, that is definitely going to make 45-degree angles for this red right triangle now. And we'll get this hypotenuse distance, again, from using the Pythagorean theorem. This is 1 squared plus 1 squared equals c squared, and when you solve that, it tells you that the hypotenuse is root 2. Okay, so having constructed this right triangle with a 45-degree acute angle, you can compute any of the trig ratios for the 45-degree angle now. I won't try to compute them all, but you can, because you know all 3 sides. You can compute any ratio that's requested. Let's see, cosine adjacent over hypotenuse. So that's, it depends on which the 45s you're looking at. Let's say we're looking at this lower left one. Then the adjacent would be 1, and the hypotenuse would be root 2. And that's a perfectly correct answer, and I'm perfectly willing to accept it, but just to keep in pace with what most people will write that as root 2 over 2. If you rationalize this, if you multiply this one top and bottom by root 2, this is what you get. Again, you can compute any of the trig ratios for 45 degrees using this triangle now. Okay, the other 2 angles, well, the good news is they come together. Again, to compute the trig ratios, what we need to do is get a triangle that has these angles as the acute, a right triangle that has these angles as the acute angles. And the clever idea this time is to take an equilateral triangle that's 2 on each side and drop what's called an altitude. Okay, so it was an equilateral triangle, all angles equal, they have to add up to 180, so this is in the equilateral, all of the angles were 60, and when we dropped this altitude, it's called an altitude, we cut the angle at B in half, so this became a 30. So this is good news. This little red triangle now has both an acute of 30 and an acute of 60. The side length of the equilateral triangle, this was 2, so when we dropped the altitude straight down, this became a 1, and again this third side is just going to be the Pythagorean theorem. So the Pythagorean theorem now would say 1 squared plus b squared is equal to 2 squared. And when you solve that out, you get that the b is square root 3. Okay, this is great news. We have our little red triangle with acute of 60 and 30, both identified. So we can compute the trig ratio for any of the trig ratios for either of those two angles now. Let's try sine of 60. So 60 right here, the sine is opposite. Opposite 60 is root 3, so this would be square root 3 on top, and the hypotenuse is 2. Maybe let's just do one more. Let's compute the tangent of 30 degrees. Okay, so the acute angle is up here now. The tangent is the opposite, and the opposite side here over the adjacent. So the opposite to 30 is 1, and the adjacent to 30 is root 3. So this ratio is 1 over square root 3. Okay. Now, these values for trig functions at 30, 60, and 45, our book calls these special values of the trigonometric functions, and they're listed out here in this table. So, in your calculus course, unless things change drastically, based on the instructors that I know, you will be expected to have these values memorized. That you're supposed to know. If somebody asks you, what's the sine of 30? You're supposed to know right away it's a half. Now this class is online and it's open notes, so you are allowed to have this table in front of you if you so choose. But in order to prepare yourself for calculus, I really suggest that you make a concerted effort to begin to memorize some of these values. So I'll try to give you some tips on how to memorize the table or organize the table in a way that maybe isn't quite so rote. And the first tip that I would have is that really all you want to try to do is learn the sine and the cosine values. Up here it's listing out all 6 of the ratios, and that seems kind of excessive. If you learn just the sine and the cosine, and then keep track of how the other 4 trig ratios can be computed in terms of these, then you won't have to memorize so much. Again, sine and cosine, these are the 2 of the starters, and they're actually the most important. Tangent's probably a distant third. So most of the times you'll just need these 2 values, and if you need the other ones, you can compute it using these ratios. Okay, so y is tan theta sine theta over cosine theta. Well, if you just write out sine theta is opposite over hypotenuse, cosine is adjacent over hypotenuse, the fractions cancel out and come down to opposite over adjacent, which is tangent theta. Our book is getting just a little bit ahead of itself, I think, to list out the trig values or trig ratios for angle 0 and angle 90, because technically those angles cannot appear as an acute angle in a right triangle. But we'll take care of that in the next section. Okay, using a calculator. Okay, so maybe timestamp here, which is about 19 minutes now. So kind of like the stuff we did with the logs and exponentials, be very interested most often for you to give an exact answer, but then sometimes we'll ask for a decimal approximation. And when that comes up, you'll need to go to a calculator that can compute these trig functions for you. So one quick heads up on computing trig functions using a calculator or computer is you have to be sure about whether or not the calculator is thinking that the angle is measured in radians or in degrees. So if you wanted to push pause for a moment and get out your calculator and compute cosine of 60, that would be great. Excuse me. Okay, so if you did that and your calculator told you that the answer was maybe either 0.5 or 1/2, then your calculator is currently in degree modes. it's expecting that the angles are coming to it in degrees. If on the other hand your calculator gave you this kind of decimal, then your calculator is expecting that the angles are measured in radians. And it turns out that the cosine of 60 radians is equal to this number. Your calculator's got a way to switch between modes, and you might need to do that depending on what problem you're working on, whether it's expressed in terms of angles, degrees, or radians. Okay. Solving a triangle. All right, so again, this is kind of a pre-calculus concept. We don't go out in the world and solve triangles, but it's the idea here is that you're going to be given some information about a triangle, and then asked to determine the remaining information. So the information will be about its angles and its side length. So here is a potential solve problem. Solve this triangle. It's like, why don't you just tell me what you mean? They mean that you need to find the remaining angle. Now this is a 90, so we don't need to look for this one. But you need to find the remaining angle and these two unknown side lengths. Right? So just code it in the word solve. Okay. So remaining angle. That's not right. So we're using the fact that in a triangle, all of the sides add up to 80. We've got the 30 and the right angle is already specified. And you might have just recognized this. This is a 30, 60, 90 right triangle. Okay, so the remaining thing here is to get both the A and the B. And we could actually use either of these two angles to try to compute that. I think maybe I'll just go with the sine. Okay, so, beg your pardon, with the 30-degree angle. So I'm going to look at the sine of 30 degrees, this acute angle right here, and the sine is defined to be the opposite divided by the adjacent. So that gives me try it one more time. A over 12, and from that I'm able to solve, multiply both sides by 12. I get that the side length there is 12 sine of 30 degrees. And if it's stuck in your memory, I don't know if it is yet, but the sine of 30 degrees, that was one of the special angles that we're able to compute exactly, is 1/2. So this would come down to be 6. Sticking, I guess, with the acute angle, let's just, the angle 60, let's go ahead and look at the cosine. Oh, my goodness, I'm misspeaking left and right. I'm going to stick with angle 30, and now look at its cosine. Okay, so the cosine is the adjacent side divided by the hypotenuse. Once again, just quick multiply through by 12, and we get the B is 12 cosine of 30, and maybe a little bit more obscure, this was the root 3 over 2 value for cosine of 30. I guess both of these could be simplified a little bit. This is 6 root 3 after we cancel. Okay. So a lot of variations on this type of problem. Okay, so more real-world problems, instead of the just abstract solve a triangle, are things like this. So, giant redwood, sure enough it looks giant, casts a shadow 532 feet long, find the height of the tree if the angle of elevation of the sun is 25.7 degrees. Well, the angle of the elevation of the sun might have been kind of a confusing phrase had they not included the picture for us right here. Right, so they mean as you're standing back here 532 feet away, the tip of the tree is right in line with the sun and forming this 25.7 degree angle. Okay, so just a sketch to try to abstract it just a little bit. We've got the acute angle 25.7. We could fill out this angle, but we don't really need it, so I'll just leave it as blank. we've got 532 feet here, and that h is the unknown. This one also we don't need. Okay, so we just like to find some trig ratio that identifies h along with the information that we've been given. So when we look at the angle, this acute angle, its opposite side and its adjacent side are involved in the information that we have. And so that suggests that we look at the tangent of 25.7 as being h over 532. So that h winds up, again, just clearing the denominators, being 532 times 25.7. And then this takes a calculator. And I'll do it with my machine as quick as I can here. My machine is expecting radian input, so I actually have to do a quick conversion here. I've got to take the degree input, 25.7, and convert it to radian. And if you remember, that's pi multiplying by pi over 180. Okay, so it's 256.034 feet long. That's tall, I should say. That's the height. All right. One more. Where are we? 26. Oh, yeah. Hopefully we'll be done within 30 minutes here. Okay. So, woman standing on this hill sees the flagpole. She knows the flagpole is 60 feet tall. So the angle of depression, so this is the angle from horizontal to down to the bottom, is 14 degrees. And the angle of elevation, so again, that's from the horizontal to the top, is 18. And somewhat amazingly, we're going to find out how far away from the flagpole the woman is from this information. Now, I've actually added to the little sketch that came in the book. The book did not provide this A and B, but that's what I want to look at, is A being the bottom half of the pole. It might not be half, but the lower, and B being the upper half, right? And now we've got two separate right triangles with side lengths of A and X, and this one has B and X, and we hope to work out some trig ratios. Okay, so for the top, why does that look so small? It looks too small. That's better. Tangent of 18 degrees. So in this upper right triangle, let's see, the opposite is B, the upper half of the pole, B, and the lower is X. Okay. And doing the same sort of thing in the lower triangle, tangent of 14 degrees. That's going to be opposite over adjacent. And we can solve each of these for the A and the B. All right, so just clearing out the X. Yeah, so we'll do it two steps at a time. B, X tan 18 equals B. And here we have X tan 14 equals A. Okay. The other thing that we do know about this problem, though, and you always want to look and say if you haven't used everything you're given, you got to find a way to use it. So we also know that A plus B is the total height of the pole. Okay, so what this tells us is that, which I have in the reverse order, it's X tan 14, that's A, plus X tan 18, that's the B. They add up to 60. Okay, and we're about on the close of it here. All right. I can factor out the x, tan 14 plus tan 18, and then I can divide through to get my final exact answer. So 60 divided by tan of 14 plus tan of 18. And I'll end the video there. I'll put the final answer into the PDFs if you want to go and look it up, but you should try it on your calculator first.